Okay. Welcome to the last session for today. So the session is on Oblivious data access. And the first talk is a lower bound framework for differentially private and oblivious data structures by Pino Persiano and Kevin Yeo, and Kevin is giving the talk.
All right, thank you for that introduction. So I'll be talking today about our new work on lower bound framework for differentially private and oblivious data structures. This is a joint work with my co-author, Pino Persiano. All right, so let's get started. I'll tell you guys about three things today in this talk. First, I'll define what an oblivious and differentially private data structure is. I'll explain to you our lower bound. In the last couple of minutes, I'll give you a taste of the new techniques behind our lower bound framework. All right, so what is an oblivious or differentially private data structure? To sort of explain, I'm going to use the very famous or classic primitive of an oblivious RAM. So here you have a user device or client on the right and a server on the left. In an oblivious RAM, typically, the user device typically has some private key and outsources an encryption of an array to the server. When I say encryption, I'm using encryption loosely. It's not only an encryption, usually it's a hidden permutation and maybe duplication, so on and so forth, but for intensive purposes, let's look at it like this. And what does an oblivious RAM let you do? Well, essentially let you do an operation such as read the first entry. And what an oblivious RAM will do is take this read operation, compile into a sequence of more complicated obfuscated accesses, and essentially let you get the first entry. So this is 0th index, so maybe 3 is the first entry. In oblivious RAM, one thing that I want to note is very clear is that after each operation, it sort of lets you change the private key. So for example, the device may change its private key, and simultaneously the server, it'll work with the server to change the encryption or re-encrypt various parts of the encrypted array. And when I say encryption, again, it's not only re-encryption, it can also be permutations and so forth. Finally, oblivious RAMs also allow you to overwrite entries in the array. All right, so sort of to define what oblivious RAM offers in terms of privacy or security, what it really wants you to do is, like I've written the definition here, but for any two sequences of equal length operations that could be done by the client, the adversary's view, which is created by the oblivious data structure, should be indistinguishable to a computational adversary. In short, what this really means essentially is hide the sequence of operations that are performed by the client. And when I say adversary's view, I want to make it clear what it exactly means. So here's the adversary's view in red. It contains everything that the server sees that it stores in its memory, and it also sees all the communication between the client and the server. What the adversary clearly does not see is the private key or anything in the client storage. All right, so that's, let's say, an oblivious RAM. You can also consider a weaker version of an oblivious RAM that we call differentially private RAMs. So in an oblivious RAM, like I said earlier, we're really trying to protect every operation. So really, the two sequences that it could be inputted could differ in every location. So here's an example that can differ in every location. This might be too strong, so you can consider something like a differentially private RAM, which is slightly weaker. In a sense, rather than protecting the entire sequence, we want to only protect sequences that are very similar. So here we can define it, for example, as neighboring sequences that differ in only one operation. So again, using this definition, you can go ahead and redefine everything for an oblivious RAM using differential privacy. You can get something called a differentially private RAM. The same thing sort of holds now for any sequence of equal length operations that differ in at most one operation. You want the adversary's view to satisfy this epsilon delta differential privacy guarantees. So this formula here, for those who've never seen this before, it's just used for composability. It's not something too complicated. All right, so I've described this in terms of RAMs, or what I like to call, which is really just arrays, but you could generalize these notions for other data structure problems. So for example, you can consider sets, which just check whether an entry exists or not. You can also consider things like predecessor and successor, as well as disjoint sets, that's also known as union find. All right, so when we consider these oblivious and differentially private data structures, there are two key parameters that we like to consider. One is W, which represents the size or bits of each memory word or cell in the system. So you can think of this, for example, as maybe a cache line in real life. The other parameter we like to consider is B, which is the size of the query outputs. And this typically depends on the problem. So for example, for RAMs and arrays, B will be equal to the array entry size. In sets, obviously, the output is a single bit of 0, 1, so B equals 1. You could do the same thing for predecessor and successor, where you're returning an element from a universe U, or disjoint sets when you're returning an identifier for a set, which is log n bits. All right, so we're going to be proving lower bounds. So I'm going to describe to you what the CellPro model is first. So this is the model throughout the entire paper that I'm going to be proving lower bounds. And this was introduced by, I think, Andy Yao in the 90s or even 80s. So what is the cell-probe model? It's a very simplistic model. Essentially what you do is you take the server's memory and you break it up into W-bit chunks. Each of these are words or cells. And really in this model, the only time we ever charge you any unit cost is when you're probing. So what probing really means is reading or writing from one of the server cells of W bits. So essentially whenever the client would instruct the server to read or locate or write to an entry in the cell, this would cost you, charge you unit 1 in this model. But critically, everything else is free. So you could do computation for free, you can solve your favorite NP-complete problem for free, generate and store randomness, access the client storage, everything's free. And so the good news about this is that a very weak cost model implies very, very strong lower bounds. So our lower bounds should apply to any reasonable model of computation where these things would actually be charged some cost. All right, so I guess I'm going to go through a little bit of the prior work to show you what kind of lower bounds are known for oblivious and differentially private RAMs. So the seminal work by Larson and Nielsen in 2018, they actually showed that in the cell probe model, ORAMs required logarithmic overhead, but there was this requirement that B, which was the array entry size, or the outputs, was at least as large as the memory size or the word size or cell size in the cell probe model. So to sort of circumvent this, a recent work by Komargotsky and Lin actually removed this restriction. They showed in the cell probe model, oblivious RAM still required logarithmic overhead, even when the output size B is much smaller than the word size W. So this is the state of the art for oblivious RAM. For differentially private RAMs, my co-author Pino and I showed a couple of years ago that in fact, you still need logarithmic overhead in the cell probe model for differentially private RAMs, but with the same restriction that the array entry size B or the output size is still larger than the word size. So, okay, I've sort of shown you this, so the next question should be the following, which is natural. It's what happens when you have a differentially private RAM, but the array entry is much smaller than the word size? In fact, before our work, this wasn't known. And in fact, Komargotsky and Lin actually posed this as an open problem in their paper to try to prove logarithmic lower bounds for differentially private RAMs in this setting. All right, so this is exactly what we do. So in this work, what we end up doing is proving that differentially private RAMs require logarithmic overhead, regardless of the choice of B and W. So even if B is much smaller than W, the lower bounds hold. So these are the first lower bounds known for this, resolves the open problem of Komargotsky and Lin. And in fact, one thing that's interesting is that's the first differentially private RAM lower bounds in the multi-server setting for any choice of B and W. So when I say multi-server, you can have, imagine 2 servers who are non-colluding, who each have the array, or you can sort of utilize the fact that they're non-colluding. All right, so that's good, but I promised you guys a framework, right? So one thing I wanted to note is that starting from the seminal work of Larson and Nielsen in 2018, there's been a huge amount of work on this sort of area. Unfortunately, what happens is that these techniques are pretty complicated, and each of these sort of works end up customizing very small parts of the proof to enable proving the lower bounds for their desired primitive. All right, so this is not too bad, but in general, to enable yourself to prove a lower bound here, you'd have to understand the entire technique and figure out exactly where you want it to customize. So this makes it a little bit inaccessible to the entire community. The papers are quite long and complicated, and you'd rather want a framework where you only need to customize the parts that you needed to know about the proof. So in fact, this is what we ended up doing. So we generalize all these techniques into what we call a lower bound framework for proving logarithmic lower bounds. So in particular, the main theorem of our paper essentially says that any data structure problem P that satisfies 2 pretty natural conditions, I would like to say, then this problem would require logarithmic overhead in the cell probe model, regardless of the choice of B and W. So the 2 conditions that we require, one is what we call large information retrieval, which essentially says that queries are sufficiently complex. In other words, you need to be able to have a data structure problem that retrieves information. If you had a data structure problem that doesn't return or just throws away all the information, you couldn't prove a lower bound. So that's the first condition. The second condition, event transfer probability, is sort of a proxy for privacy. And what it's essentially saying is that any event that an adversary can observe for one sequence of operations should transfer over to another sequence of operations. So this is, roughly speaking, a proxy for privacy. All right, so from this framework, we get a bunch of lower bounds. So the first result, like we said, was for differentially private RAMs. We proved logarithmic lower bounds. But in fact, using our framework, we end up proving these lower bounds for a bunch of other data structure problems, including sets, predecessor and successor, as well as disjoint sets, union find. And I wanted to note that all of these in plain text land have sublogarithmic and usually almost constant overhead. All right, so I'll explain to you guys the lower bound framework. I gave you the two conditions at a very high level, and I'm going to go to them in more detail. And in fact, to do this, what I'm going to do is show you how to use our framework for a specific example of proving logarithmic lower bounds for differentially private sets. All right, so again, this is the lower bound that we prove. Essentially, we prove that in the cell probe model, differentially private set data structures require logarithmic overhead, regardless of the choice of B and W. And how we're going to go about proving this is exactly like I said, just prove the two conditions. So here's the formal statement of the first step of condition, which is large information retrieval. So the first step of when you're trying to prove any lower bound is come up with a hard distribution. You want to come up with a sequence of hard updates that essentially will allow you to prove the lower bound. And this is what large information retrieval is saying. You want to pick a sequence of n updates, such that if you picked any consecutive subset of L updates, there exists, roughly speaking, a query set of size L, whose answers have high entropy with respect to those subset of sequences you considered. All right, that's a lot of words. It's actually not that complicated, so rather than going through this definition in detail, let's just go through a quick example. So I'm going to show you how to do this for sets. So let's suppose you have a set that stores a subset of any elements from 1 to n. And what we're going to do is, for every pair of these possible elements, we're going to create one operation. So 1 and 2 will have operation 1, 3 and 4 will have operation 2, and so on and so forth. So we'll have n over 2 operations. And then what we're going to do is generate the following random updates. For each of these operations, I'm going to flip a coin, maybe just take a random bit. And this will decide which of the two elements I'm going to insert. So here I pick C1 to insert 2. And I'm going to do this again for all n over 2 operations. And essentially, I'm going to get a sequence of insertions, where that are depending on the random bits that I generated C1 to Cn over 2. OK, so now I want to take any consecutive subset of L updates. So here I'm just going to pick the first two, so the L equals 2. And without knowing the randomness, I want to be able to pick a query, a set of similar size, that allows me to extract the entropy I use to generate the updates. Well, it's not too hard here. What I would do is, let's say I wanted to do the first two operations. I'm going to essentially send queries to check whether 1 is in the set and 3 is in the set. And in fact, for example, it's not very hard to see that this actually allows you to get back C1 and C2. So if I do query 1, I realize 1 is not in the set. It means 2 is in the set, so C1 is equal to whatever bit required to get 2. And similarly, I would query for 3. I'd see it's in the set, and I would see that C2 is equal to 0, for example. And that's actually it. So whenever you have a data structure problem, all you have to do is find this sequence of hard updates, and for any subset of operations, sort of find this query set that will allow you to retrieve this entropy. All right, so that's the first sort of step we need to do. The second step we need to do is event transfer probability. And again, there's a formal definition. Roughly speaking, it just says any event that's observable by an adversary for one query should be observable with some reasonably similar probability for the second query. All right, so how do we do this for differential privacy? This is literally the proof. You just rearrange the formula. And in fact, what I was going to say is, we provide generic lemmas in the paper for any of these standard notions of privacy. So obliviousness, differential privacy, encrypted search, or multi-server variants of any of these. So if you want to use our lower bound framework for any of these privacy notions, you can just use the lemmas directly from our paper. The reason we put this in specifically is it allows you to extend the lower bound to other privacy notions that aren't the standard ones. So in particular, if you wanted to prove a lower bound for a privacy notion that's either incomparable or weaker than any of these 4 things, then you can try to use the event transfer probability to prove it. All right. OK, so one thing I'll say is that specifically for this lower bound for differentially private sets, we showed that in the large information retrieval that we could extract v equals 1 bits for each of the L updates on average, right? So if you wanted to use our lower bound framework more generically, in fact, you can consider there are problems where you can extract more than 1 bit, generic v bits per update, in which case you would get this lower bound. So you can see that you immediately get the set lower bound by setting v and b to equal 1. All right, cool. So one may ask, I gave you this framework, is it tight? You're going to try to use it, but are there data structure lower bounds where you can prove logarithmic lower bounds, but not in our framework? So we actually considered this. So one problem that we considered are stacks and queues, which cannot satisfy this. It's not hard to see because if you insert items into a stack or queue, any consecutive subset in the middle, you're not able to extract the information out. So it wouldn't fit into our framework. But it turns out it was an interesting question because for oblivious stacks and queues, logarithmic lower bounds were known when b is larger than or equal to w. And when you have differentially private stacks and queues, it's known that you need log n overhead only. So one open problem we had was, what is the override overhead for Oblivious stacks and queues when the B is much smaller than W? Because it'd be really bad if you can prove a lower bound here, but it wouldn't fit into our framework. So we end up showing actually when B is much smaller than W, Oblivious stacks and queues require smaller than log n overhead. So in fact, it's inherent that Oblivious stacks and queues cannot satisfy our framework because you shouldn't be able to prove this lower bound. And in fact, this result is actually the first separation for online Oblivious data structures between settings of when B is greater than or equal to W and B is less than W. All right, so I think in the last minute or so, I'll give you a little bit of a taste of the proof techniques, mainly because I'm running out of time. I won't be able to give you too much, but let me see if I can. So what we do is we build off the chronogram technique by Fredman and Sachs that was introduced in the 90s, actually. In terms of Oblivious or cryptographic data structures, it's been used twice in the past. So one is actually my work, or my previous work with Pino here that showed logarithmic lower bounds for differentially private RAMs when B is greater than or equal to W. And in fact, the techniques we use here build on top of that paper. I'd also like to note that it's also used to prove super logarithmic lower bounds for statistically oblivious near neighbor search as well. So, but that technique is slightly different. So the specific techniques here build on top of the first paper. All right. So the main new proof technique we use is the fact that, so most of these lower bounds, what they end up doing is showing that when you encode a data structure, you're trying to find an encoding of a data structure that answers like that sort of encodes the database in an impossible way when queries and updates are too efficient. And in particular, the new core technique that we've proven here is that we show that the majority of answers to queries can be encoded for free as long as you're assuming a data structure is too efficient to be true. So at a very high level, it's not a very complicated sort of concept. Take a data structure that's too efficient to be true. Maybe it only updates 2 cells on updates. So for any update, it updates 2 cells. Now let's say you take a random query. You're gonna pick a random query and to see which cells it probes. And let's say it probes these cells. Well, in fact, you realize that if the data structure is too efficient to be true, these are not gonna overlap. These cells probably won't overlap. So in other words, if you have a small subset of updates, they only touch a few number of cells when they update. If you pick a random query later, it won't change the answer. So in other words, even if you don't know the updates, you can still get the answer to a random query for free. And this is sort of the core technique we use to prove our lower bound in our lower bound framework. All right, so that's very high level. I encourage other people to look at the proof or ask me questions if you have any more ideas about the proof techniques. And thank you all for listening. I'm happy to answer any questions.
Thank you. So is there any question? So if you have a question, please stand up and ask it using the microphone.
Hi, Kevin. Thanks for the very nice talk. I wonder, so in the lower bound, it's very important that the comparison between B and W, right? So I wonder, is B the return bit numbers? Is it right?
Yeah, so I guess, yes, it's essentially the output, the size of the query output.
So I wonder, like, is B, the size of B is inherent for every data structure? For example, in the set example, you said that B equals to 1, but actually, if every time you just return more information, that like.
But that makes, so what you want to do is, yes, you're right. If you consider a data structure that's more complicated, it's easier to prove lower bounds, right? So when you have a set, it only returns a minimal amount of information. It makes you proving lower bound harder because it's easier to design data structures for it, right? So in fact, in a lot of the cell probe lower bounds, the smaller the output, so let's say B equals 1, which is minimal, the less information you get, which means it's easier to construct data structures, but it's harder to prove lower bounds for them.
Oh, so you cannot like get better lower bound by increasing returning information?
You can, but that's a different problem you're proving for, right? Let's say, like a set, I don't know, maybe you can return, like let's say an augmentation of the set problem is I return not only the item is, whether this item is in the set, but the login items around it are also in the set, right? That makes the problem harder, right? If you're designing a data structure, this makes it a lot harder, but it makes it a lot easier to prove lower bounds actually, because the problem is harder. So B equals 1 is usually the hardest case, and that's why it requires more work to prove lower bounds.
Thank you.
Okay, so let's thank Kevin again. Okay, welcome again. Second talk is lower bounds for batch PIR with private preprocessing by Kevin Yao, and Kevin is giving the talk.
All right, thank you for the introduction. If I bored you the first time, I'm sorry. I'm going to bore you again, but let's go. All right, so I'm going to tell you guys about a different work, lower bounds for a different primitive of batch peer with private preprocessing. All right, same outline. I'm going to define to you what batch peer with private preprocessing is. I'll explain to you our contributions, and I'll give you more of a taste of the lower bound proof technique this time around. And throughout this talk, I'm going to leverage my previous talk, so it's good to know the schedule. All right, so private information retrieval. If this picture looks familiar, it should. Again, you have a client on the right, and then a server holding an entry database on the left. What's going to happen is the client will get some index I. It'll do some sequence of obfuscated accesses to get the entry, and it should do it in such a way that the server doesn't know what was the requested index. All right, so now you might be asking, all right, this looks identical to ORAM. What's going on, right? It should look identical to you right now. So leveraging off my previous talk, I'm going to give you a quick comparison between what a peer and an ORAM is. So it turns out there's one subtle difference that makes PIR much more challenging to sort of construct, but also it makes it easier to prove lower bounds. So in PIR, which is on the right, what ends up happening is the server must create one encoded database that is allowed to be accessed by multiple users. So in other words, what I'm trying to say is that this encoded database is not going to be specific to any private key that the users will hold. In contrast, for the ORAM on the left side, what's going to happen is the server and the client will work together to generate an encrypted version of the database that works specifically for a specific private key. So in other words, what ends up happening is you have a database that works sort of for one user with one private key. Of course, you could generalize it to multiple users, but in an ORAM, it's still critical that they all share the same private key. So in other words, this is harder, right? PIR is a harder problem because the server can't leverage a private key to make accesses faster. And in fact, this is what ends up happening why PIR is usually much more expensive than ORAM. But that's good for us because I'm proving lower bounds, so that makes it easier. I can prove higher lower bounds. All right, so and as an example here, before I was proving logarithmic lower bounds, but it turns out Bimelish and Malkin in 2000 proved in what's called the standard peer model, I'll get to it later, the server computation must be linear. In fact, you must touch every entry in the database. So again, linear versus logarithmic. So this is pretty bad, actually, right, in a sense. If you have to touch the entire database for each query, it's pretty inefficient. Luckily, there were two ways shown to circumvent this linear lower bound, and I'll talk about them here. So one is called peer with preprocessing, and another is called batch peer. And both of these actually enable us to get sublinear server computation per query. So okay, the first one is what I'm going to go through is called peer with private preprocessing. So the settings should look the same, except there's now a preprocessing stage where the client and server can work together to compute some hints without knowing the queries coming in. So it's preprocessing. You don't know the queries yet. So what we'll do is the client and server work together to create some hint. This hint should be private. So in a sense, the only person that ever learns the hint should be just the user. And even though the server may help to compute the hint, the server should not learn what the hint is. All right, so that's the preprocessing stage. And in the query stage, you still get the index I, which the user didn't know before. It's still going to do its set of queries. It's still going to do its obfuscated access. But it can now leverage this hint to try to make the query stage faster. In particular, try not to touch the entire database per query. So when we consider peer with private preprocessing, we're going to consider two complexity measures. One is the hint size, which let's say is R bits, and the computational time, which essentially is the number of entries T that is probed by the server during a query. So it turns out peer with private preprocessing is sort of a generic name that has been studied under many other different names, so like doubly efficient peer, private stateful information retrieval, and more recently offline-online peer. But the really good news is you can get very, very sublinear time. So in the seminal paper by Corrigan, Gibbs, and Kogan in 2020, they showed that there exists a construction where the product of the time and the hint size is linear. So if you sort of rearrange it, you can figure out that actually you can make both the hint and the time be square root n, essentially, which is very, very sublinear. And in fact, Corrigan, Gibbs also proved a lower bound. Corrigan, Gibbs, and Kogan also proved a lower bound, showing that the product must be essentially n divided by polylog n factors. All right, so this is one way to get sublinear server time, which is great. Here's another way. Let's consider batch peer. So this is a very famous primitive, probably most people know about it. But rather than having one index, you're going to have a batch of k queries to do at once. And the goal remains the same. You want to get all k blocks, but it's critical that the batch is given to you ahead of time. So before the user is going to start its query, it knows all k indices that it wants to query for. So here it turns out that in 2004, Ishai, Kushlevitz, Ostrowski, and Sahai, they use these things called batch codes, but they show that you can actually have a construction for k-query batch peer with time that's like only a polylog factor higher than single query. And this is really amazing, right? So like this sort of polylog overhead is independent of k. So now what you get is amortized server time per query is order n over k, but let's say k is equal to square root n. This is very sublinear, actually. So okay. These are two ways to sort of get very sublinear server times, but they have sort of the limitations. But regardless, it's an interesting question of, can you combine them, right? We have two ways of doing this. Can we combine them to make server time even faster? Okay, so what do I mean by combine them? Like, what would the dream be? So here we have, I've sort of populated on the left the two things that we knew. So sort of for single query, we know that when you have no preprocessing, single query requires linear time, and k-query you essentially get for free, ignoring log factors. So we could imagine the same thing would hold for, from single query to k-query private preprocessing here, where you would essentially get this for free as well, ignoring polylog factors. It seems like it's a reasonable thing to hope for, and in fact, I was hoping to do this. I actually tried to construct this at first, but I guess I gave away the answer in the title, but the answer is sort of, this is not possible. So this dream doesn't hold, and in fact, the main contribution of this work essentially is that we prove for any computational secure k-query peer with private processing, even for constant non-colluding servers, it really must be that the product of t times r is equal to omega n times k. So remember, for single query, we had that t times r is equal to order n. But somehow, when you want to do k-query simultaneously, it becomes the same as just doing k of them in sequence, the trivial sort of approach. I'll also note that the condition of when the hint size is less than k, this sort of encompasses the fact that you can always just run a batch peer in linear time. So sort of if the hint is too small, then you can always run batch peer, but that still requires linear time. So like I said, this lower bound is pretty encompassing. It holds even when peers have constant error, and it holds in the multi-server setting as well. Okay, so one corollary of this is you could plug in k equals 1 to get a single query lower bound, in which case you would get t times r is equal to omega n, and this immediately improves upon the prior single query lower bound by polylog n factors by Corrigan, Gibbs, and Kogan. And in fact, this is exactly tight, because if there's one construction of Corrigan, Gibbs, and Kogan, if you look at the sort of the parameters carefully, you can actually construct something where t times r is equal to order n upper bound. So this is a tight lower bound. Okay, so I'm telling you lower bounds, but I didn't tell you the model I'm proving them in, so let me try to pay my debts. In the standard peer model, this is different than the CellProbe model. So this is the standard peer model that was introduced by Baimel, Ishai, and Malkin in 2000, and it essentially uses what's so-called a non-encoding assumption. In particular, the server can only do sort of two permitted operations. The first is it can arbitrarily replicate its database. So it can take the database and copy it for a second copy. The other thing is it can permute it arbitrarily. But these are the only two operations that are permitted. In particular, something that's not permitted is arbitrary encoding. So you can't store the XOR of blocks in any place. Okay, so this is what the server's restrictions are. I'll note that the client has no restrictions, so the hint can have arbitrary coding. You can do whatever you want. It just has to be at most r bits long. So again, leveraging off my previous talk, I can compare the standard peer model with the CellProbe model. So in the standard peer model, really what you're doing is replicating and permuting, so each original block has to be stored as is in any arbitrary location you want, whereas in the CellProbe model over there, I've thrown random equations there. You could do whatever you want, right? You could store whatever you want. So obviously, you'd rather prove lower bounds in the CellProbe model than the standard peer model, because if the CellProbe model is all-encompassing, whereas the standard peer model is a little, let's say, it's very restrictive, even though it actually does cover a lot of known peer schemes. So okay, so one thing we actually prove in this paper is a barrier. So this goal of trying to prove these lower bounds in the CellProbe model will end up being extremely difficult. Because what we prove is that if you ended up doing this, you prove the same lower bound in the CellProbe model, what you end up doing is proving that the online matrix vector conjecture is true. So for those who don't know, the online matrix vector conjecture is like a core tenet of fine-grained complexity. People have been studying it for decades. They have no clue how to prove it. And I find it very unlikely that you end up proving it through pure lower bounds. In other words, this seems like a very fundamental barrier that would be hard for us to prove. And that's why it makes sense to study the standard peer model as well. All right, so finally, I guess one thing I'd like to note is to complement all these lower bounds, we prove an upper bound saying essentially you can take a black box reduction from any single query peer with prior processing and construct a batch version of it with essentially K overhead. And it's not too complicated, it's just via batch codes, but it's interesting because the prior reductions known require either multiple rounds or certain assumptions on the single query scheme, whereas ours is a black box sort of construction. All right, so I'm going to get into lower bound proof techniques now. How do we actually prove this lower bound? And we do this in 3 steps. The first is what we're going to do is develop a relationship between queried and probed entries. I'll go through exactly what a queried and probed entry is later. The second thing is we're going to come up with a hard distribution, which is discovering good batch queries. And then finally, like I said, the standard technique we always do in proving lower bounds is find an impossible encoding of a database. So because the last is sort of a standard technique using data structures, I'm only going to focus on the first 2 in this talk due to lack of time. All right, so when what we want to do is develop a relationship between queried and probed entries. So what is a queried entry? Well, these are the queried entries. Essentially, these are the entries that you're given in your batch of queries that you want to retrieve, that the user wants to retrieve. And what are probed entries? So probed entries are, when you have this batch query, you execute your peer scheme, and you're going to end up sort of having to touch certain blocks in the server memory. And this is what we call the probed entries. So here is where we're going to use the standard peer model, actually. In particular, the standard peer model allows the server or the adversary to see that when you touch a certain block, you can correlate exactly to which entry it was being touched. So here I know the second entry was being touched. In the cell probe model, we can't do this because of, for example, this block could be the XOR of 3 different entries, and I wouldn't know which one to attribute it to. So we need the standard peer model here. Okay. So, yeah, all right, I guess. The whole point of what we're trying to prove is now, if 2 is, let's say you have 2, which is in the queried entry set, what is the probability that 2 is also probed on the server side? So to do this, what we're going to do is make an assumption. We're going to suppose that the scheme touches at most half the entries in the database. This is without loss of generality, because if you touch the whole database every single time, we already proved our lower bound. And the question we want to ask essentially is, if index I is queried, what is the probability that the if entry is also probed? So it turns out that it's not very hard, actually. Let's say we're taking an information theoretic approach to privacy. And here, 2 is in the queried set, but 2 is also in the probe set. But if you're considering information theoretic privacy, as soon as I flip 2 to 1, the server's view shouldn't change, right? In which case, essentially, the set of probed entries should also not change with high probability. Otherwise, the server will be able to detect. So this is true information theoretically. It turns out it's not very hard to sort of put it to the computational setting as well. So I said a lot of words. What does this really mean? What I'm essentially saying is the probability of whether index I is probed is really, it almost should be independent to whether index I is queried or not. So in particular, the probability that index I is probed, given that index I is queried, is nearly identical to the probability that index I is probed, given that index I is not queried. In other words, whether index I is queried or not should not depend on whether it's probed. Okay, so why is this useful? Yes, this seems like a cool privacy result, but it turns out what you can end up doing is now, by applying Markov's inequality, you can sort of see that the expected number of indices that are queried and that are also probed essentially is only going to be half. So half of the queried entries will be probed. And this actually gives you a very neat idea to do a compression scheme, essentially. So let's suppose, again, I have this batch query. I only probe these entries on the server. By correctness, my peer scheme says essentially that the client should be able to retrieve all the entries in the batch query. In particular, they have to be able to retrieve entries that were not probed, right? In other words, you're getting these entries for free, almost, right? Essentially, all I have to use is the probed entries and the hints, and magically, I have a scheme that's producing entries that I did not probe and that are just in the query set. All right, so this is what we want to do in the lower bound. We want to find compression schemes. So let's try to push this, right? Let's say we did it once. We ran one batch query. We were able to get B1 and B223 for free. Let's do it again, right? With this, we want to find a hard distribution. We want to be able to keep compressing the database. So we could run this again. We have another batch query. We run the peer scheme. We find all the probed entries, throw away everything else. Now we use our peer protocol, i.e. a compression scheme, to get more entries for free. All right, so here's a bad example. If I just do this arbitrarily, it's very possible that the free entries I get are the same every single time, right? I'm not really compressing here, essentially. So this is what I mean by discovering good batch queries. What we really want to do is find a sequence of batch queries that when you run it, the free entries that you get are minimally overlapping over time. So for example, that was a bad thing, but this would be a good one. If you say, for example, ran this scheme again and you got B2 and B117 for free. So this is one of the key arguments we need to do in our paper, and essentially we prove that, in fact, if you just do random batch queries, it satisfies this property with very high probability, and the argument is via some combinatorial counting arguments. All right, so given the first two steps, what you're now going to do is you have a compression scheme. Each of these batch queries is letting you encode free entries for free, and all you're going to do is put it together and give an impossible encoding for the database. And in a sense, what I would like to point out specifically is that you can see that the compression scheme is directly correlated to how many entries you probe, which is T, and the size of the hint, which is R. So essentially, this compression scheme will take this T and R, and if T and R are too small, it'll give you an impossible encoding of the database, essentially. This is a very high-level sketch of the proof. I encourage you to take a look at the paper or ask me any questions if you have any more, and I think that's the end. Thank you for listening, and if you have any questions, I'm happy to answer.
Is there any question from the audience? Yeah.
I was just wondering, you said earlier that if you could prove a lower bound in a cell probe model, then this fancy conjecture would be true. Is there any hope of getting the opposite? I mean, if that conjecture was true, could you prove a lower bound in a cell probe model, or is that just out of the question?
Very good question. So at a high level, what we end up doing is how to prove this lower bound is you take the two-server here, and essentially you notice there's like the very first one that arranges it in a square root n by square root n matrix and does matrix vector multiplication. So essentially what the online matrix vector does is it proves that you can't do this very fast, but if you assume it's false, you get a very fast algorithm, you just plug it in directly. So I'm not sure the other way would hold, but it's a very interesting question to see whether they're equivalent or not, actually. It's a very, very interesting question. I wouldn't know. Yeah.
Any other question? Yeah.
In your first talk, you showed a framework. Do you have a framework for your second talk? I can see your conditions in your first talk doesn't hold anymore in the second talk. Otherwise, there's no point for second talk. But
good question. I'll get back to you. I don't know. I actually don't know. I guess for PIR, other weaker notions haven't really been studied, in a sense. I think differentially private information retrieval has been studied, but I think you can actually construct much better things there. So it's very possible. Like the reason the framework worked is that, I don't know, ORANs, for some reason, whatever weaker privacy notion you try, like I've tried, it always ends up being logarithmic overhead. That's why I end up proving all these lower bounds. But for PIR, maybe it's not the case, so maybe you couldn't even get this framework. I wouldn't know, actually. It's a very good question to explore. Yeah.
Okay, let's thank Kevin again. Okay, so the last talk for this session is how to compress encrypted data by Niels Fleischacker, Kasper Green-Larsen, and Mark Semkin, and Niels is going to give the talk.
Yeah, thank you. So, how to compress encrypted data, and what do we mean by that? Basically, the problem is the following. We have a very long list of encrypted values, and what we want to do is basically take this long list of encrypted values and compress it down to a shorter list of encrypted values. The problem is that information theoretically, in general, this shouldn't be possible, right? However, we know a lot about this vector that we want to compress there. What we know about this vector is that most of the encryptions are actually encryptions of 0. And that gives us a lot of structure to work with. So what we want is that we can take this vector, which is actually a vector that contains mostly zeros. We want to be able to compress it without knowledge of the secret key in such a way that at the end we can basically decompress it again, now knowing the secret key, and get the plain text vector back, including all the zeros. So why would one want this? Well, there are many cryptographic protocols that actually contain such a subprotocol where they do this. One example is encrypted search. For example, in the paper by Choi, Dachmann-Solet, Gordon, Liu, and Yerokimovic, where basically Alice has a large database of encrypted values and encrypted under a secret key that is only known to Bob. Now, Bob basically sends encrypted search terms to Alice, and Alice now wants to give the results for this search query. So these encrypted values, they are encrypted under a homomorphic encryption scheme, in this particular application under a fully homomorphic encryption scheme. And Alice can basically filter this very large database in such a way that all the messages that do not match the search terms are set to 0, and the other ones are retained. So if only very few terms basically match the search terms, we can now apply the compression scheme, and what we get is a much smaller message to send, because otherwise Alice would basically have to send something that's in the size of the entire database. One important thing here is that in this compression step, even though FHE, for example, is used in this application, we do not want to use homomorphic multiplication because that's expensive. So what we focus on is compression that only uses an additive homomorphism. And on the receiving side, Bob could now just use his secret key to decompress and learn what the matching search terms are. Okay, so how could we be able to do something like this? There is a conceptually very simple construction that is based on sparse polynomials. Basically, we have our very long list of ciphertexts, and we can interpret the messages in those ciphertexts as the coefficients of a polynomial. And if we do that, one thing we can note is that since most of those encryptions are encryptions of 0, this polynomial is very sparse. It has only very few non-zero coefficients. Now, there is a fact about polynomials that most people who had high school math should know, that if we have a polynomial that is of degree t, then you can uniquely interpolate it from t plus 1 points. There's a bit less known fact about sparse polynomials that is very similar. If you have a polynomial that is t-sparse, meaning that only t of the coefficients are non-zero, then we can uniquely interpolate it from 2t plus 2 points. So we need twice as many points, but it works. So how can we apply this here? One way we can apply this is taking this polynomial, evaluating it only uses an additive homomorphism. So we need to add and we need to multiply by constants. And so we can evaluate it on 2t plus 2 points. And now we have a list of ciphertext that has only length 2t plus 2. So this is basically an O of t. And we can just view this as the compressed form of our very long vector. And this compression is, in fact, asymptotically optimal, because we only have O of t many ciphertext now. And this is strictly needed to convey O of t, well, exactly t values. Okay, so how would this work? Then we basically send this over to Bob in the application, and Bob can use decryption to get, well, 2t plus 2 evaluations of the polynomial, and can then apply the interpolation algorithm to get the full plaintext vector back. Now, as I said, the compression here is actually asymptotically optimal. The computational costs are not quite. So the evaluation, if we would do this individually, would be pretty expensive. We can do it more efficiently by applying a fast Fourier transformation. However, it's still, it's fine, but not super efficient. The interpolation, on the other hand, is super expensive. If we try to do this, what we end up with is a cost that scales with the square root of n, where n is the size of the entire database. Since the database could be very, very large, this can become impractical very quickly. So this is a theoretically nice and conceptually simple way to do it, but we would be looking for something more efficient. So we have another solution that is based on so-called invertible Bloom lookup tables. Invertible Bloom lookup tables are a set membership data structure that was first introduced by Goodrich and Mitzenmacher. And the idea of it is basically that we have a sequence of values, say M1 through M4 out there, And what we want to do is we want to encode them in such a way that the size of the encoding is independent of the length of our sequence. But if our sequence is short enough, then we can completely decode it again. So how does an invertible Bloom lookup table or an IBLT work? We basically have, in the simplest form, we have two matrices. On the left-hand side, we have our value matrix. On the right-hand side, we have our count matrix. And for each row in the matrices, we have a separate hash function. Now, if we want to insert M1 into this matrix, what we do is we plug M1 into the hash function. The hash function tells us a position in the row of the matrix. And at this position, in the value matrix, we just add M1. And in the count matrix, we just increase the value by 1. So we add 1. So we do the same thing for M2, we do the same thing for M3 and M4, and we end up with this data structure. Now we're supposed to be able to decode this again. How does that work? We just look for a 1 entry in the count matrix. A 1 entry in the count matrix means that only a single entry was put into this position. That means in the value matrix, you will find something that was actually in our original sequence that we're trying to reconstruct. So we can take this value, plug it back into the hash functions, we learn where it was inserted in all of the rows of the matrices, and now we can remove it. So this helps because now we have more 1 entries in our count matrix so that we can keep on going and decoding this whole thing. So why is this helpful? Well, oh, right. So first of all, this successfully decodes with probability 1 minus 2 to the minus epsilon if there are at most t elements in there. And this only requires addition and not particularly many of them. So the idea is now that, well, can't we just do this under homomorphic encryption? The idea being that if we insert a very long list of messages, but most of them are 0, into this value matrix, it is the same as if we had not inserted those 0 values at all, as if we just inserted a small number, say t, of non-zero values. So we can try to do that. As a first attempt, we can basically first now look at the value matrix on its own. We have now 4 ciphertexts instead of 4 messages, and we try to insert them in there. So we take C1, we plug it into our hash functions, we get positions, we add the ciphertext to the corresponding positions, and we do the same thing for all of the other ciphertexts. We send this thing now to Bob as the encrypted version, as the compressed version of our very long vector, and Bob knows the secret key, so he can decrypt this. The nice thing is now that wherever there's a 0, so C2, for example, here's an encryption of 0, basically this message just disappears. In this center cell here, even though we inserted 2 ciphertexts there, after decryption, there's only a single message in there. So we could now try to remove it from the data structure. The problem is that to know where we need to remove it, we need to now put the correct thing back into the hash functions, but the hash functions took the ciphertext C3 as input, and we no longer have C3 because, well, we did this homomorphic computation, so this ciphertext is gone now. There's an additional problem, which I basically hid by not showing you that we also need to compute a count matrix. We don't actually know how to do this, because we need to somehow identify which of those cells only contain a single value. And if we were trying to maintain a count matrix, we would need to evaluate this predicate that tells me that a message is non-zero. And we cannot easily do this using only an additive homomorphism. So what can we do? We use something else. We use a tool that we call a wunderbar pseudorandom vector. And what it is basically just a vector that associates an index with pseudorandom values. So far, that's pretty simple. We can easily do that. We can just store a long list of pseudorandom values. However, we want it to be wunderbar, and that means that it should have a short description, meaning it should basically only be described by lambda many bits. And we also want to be able to efficiently go from the index to the pseudorandom value, and then from those pseudorandom values, which are actually unique, so they don't repeat in this sequence, we want to be able to go back to the index efficiently as well. So how would we want to instantiate this? Well, if we ignore a bunch of details, this is essentially just a PRP. Basically, the PRP is described by a short key of size, for example, security parameter many bits, and going from the index to the pseudorandom value is just applying the PRP, and going back is just inverting the PRP. So that works fine. So how does this help? Now, to the real deal, the actual construction. We again have two matrices, and now we want to insert C1 again into this data structure. What we do now is we don't hash C1. Instead, we only look at the index. So we hash 1. We get positions. On the left-hand side, in the value matrix, we still just insert the ciphertext. On the right-hand side, in what I will call the key matrix, we insert K1 times C1. So this is the ciphertext multiplied by a constant, where the constant is just the field value the PRP applied to the index. So the PRP applied to 1 basically gives us K1. And we do the same thing for all of the other values. And now this is our compressed representation of our vector. And we send this to Bob. Bob still has the secret key. Bob can decrypt. So this still has the same nice property. If one of the messages, in this case M2, is 0, basically it just disappears from this data structure. In this center cell, we basically, on the left-hand side, we only have M3 left. On the right-hand side, also because we had K2 times M2, but M2 turned out to be 0, well, the whole thing is 0, so it just disappears. How can we now tell that this cell only contains a single value? What we can do is we can take the value in the right-hand matrix, and we can divide it by the corresponding value in the left-hand matrix. If there's only a single value in this cell, what we will get is simply K3 in this specific case. And we can then apply the inversion, we can basically apply the PRP to get back the index 3, and then we can check if this index falls in between 1 and n. And if there are more than one element in this cell, then with overwhelming probability, it will fall outside of this range. Therefore, we can now say, okay, this falls into this range, so this is probably one of the values we're looking for. So now we have the index of this value, which means we can plug this index back into our hash function, and we can then find out what the positions are and remove the value from our data structure. And this, again, frees up our matrices, and we can basically go on decoding it. And again, this basically is successful with probability roughly 1 minus 2 to the minus epsilon. And if we want to actually send this as an encoding of our ciphertext, we have to think about all the other things that we need to send. Basically, what we need to send are these two matrices, a description of the PRP, which is just the PRP key, but also these hash functions. But these hash functions can just be replaced by a single PRF, so this is also not a problem. OK, so how does this compare to previous work? As I said, there are a bunch of cryptographic protocols that essentially contain something like this as a subprotocol. And the first one we have here is by Akavia, Feldman, and Schau from 19. They were basically able to compress to t² log n, which isn't particularly great because it still scales with the size of the entire database, and also t² can be pretty large, if even for modest sizes of t. And also compression and decompression in their case is pretty expensive. Then there was work by Liu and Tromer. They were basically able to do something, well, comparatively much better. They were able to compress to epsilon times t log t, but still compression and decompression is pretty bad. And then there's the work I already mentioned by Choi, Dachman, Solet, Gordon, Liu, and Yerukimowicz. And they were able to do something much better. They were able to basically get to epsilon t as a compression, but also the compression and decompression algorithms are much more efficient. So this is basically the baseline that we're trying to break. And our polynomial construction basically is much better in the compression rate. We only need to send O of t many ciphertexts. The compression is not terribly efficient. It is not completely impossible, but not great. But decompression is really bad. This is really inefficient. Like, it's polynomial time, but that's about it. Our IBLT construction is much better in the computational department. So the compression and decompression are very efficient there. And the size is smaller than the best previously known construction. Basically, so we divide by log t there, which makes it, well, for some size of t, that makes it significantly smaller. And the very good news is that in very recent work of the same authors that will be on ePrint very soon, we are basically able to give a new construction of IBLTs that is much more space efficient, and that allows us to bring this size down to actually epsilon log epsilon plus t. So now we no longer multiply epsilon with t, which basically gives us a much better compression. And with that, I'm done. And if you have questions, I'm happy to answer them.
Is there any question from the audience?
Hi, very nice talk. So I was wondering first, what kind of requirement does your compression technique need on the underlying encryption scheme, in addition to being additive homomorphic?
So it needs to be additively homomorphic over some field, technically. We need to be able, so in this IBLT construction, we need to be able to do this division. So we need that we can actually divide by this value. So we need to be able to invert it. So we need it to be a field, although something like Payet would work, where we technically work in a ring, but because you cannot detect that it's not a field, you would still be able to do it.
I see. And also, can you elaborate on the application again? Because so typically with the application of homomorphic encryption, only one party will have the ability to decrypt. So in this case, kind of one party will encrypt and decrypt at the same time, and the other party does the evaluation. But for the decompression, do you need the receiver to also decrypt?
So I'm not sure I completely understood the question. So the scenario is basically that we have, in all of the scenarios with this, basically we have two parties. One of them has a bunch of encrypted values that it may, for example, filter, or maybe for some reason there are already many zeros in there. And the other party has the secret key. So on the side that decompresses, the secret key is always known. Mm-hmm. So, and it is not necessary for the compression to know the secret key. So this is just the setup for it. I'm not sure I understood the question.
I see, yeah, we can take it offline. Thank you. Yeah.
Okay.
Hi, very nice presentation. I was just wondering if we can do this, but for things that are not zeros, like any other number, would it still work?
Sorry, I couldn't hear you.
So if we have encryptions of ones, so if we have like a database where there's a lot of encryptions of one instead of encryptions of zero, can we still compress with that?
So you have lots of encryption of one. I mean, maybe we can just subtract one, then we have lots of encryptions of zero, and then we can do the same thing and add one again. I think that should work.
So it's not like defined to...
I mean, I think if you have, it should be generalizable to basically any particular value, because you can just shift things to zero and then do the same thing.
All right, thanks.
Thanks for the talk. I wanted to clarify whether the party who compresses the data knows T, whether the party that compresses the data knows how many non-zeros there are in the vector.
So there is basically, we need to know an upper bound on the number of zeros. You can do the same thing if this upper bound is violated. It will just, compression will fail with high probability in that case.
So the party who
in the case of the polynomial construction, it will fail with almost certainty. you will basically get something completely different. In the IBLT construction, there is a chance that you will get back the correct result, but the probability goes down significantly as soon as you go beyond basically the threshold.
And so the party that compresses data has no way to check whether compression has worked, right? It's
right.
Just
they have no way to check it. This is basically why it is possible to do this at all. It's basically because normally when you do compression, right, there's some things are get smaller, some things need to be expanded, otherwise you cannot do compression of arbitrary data. But this is not arbitrary data, so we do something else where we're just saying that if basically the condition is violated, decompression will fail, but the person who compresses has no way of knowing whether that happens or not. Yeah.
Okay, thank you.
Okay, so let's thank all the speakers of this session.